This is Cedric Villani speaking from Paris. Delighted to be here as part of this 14th International Conference on Mathematical Education. It's my pleasure to address a large audience. All my life has been devoted to sharing and transmitting knowledge, experience, advice. And in particular, today, I'm addressing to young participants of this ICME to talk about mathematics in the society, such an important, constantly renewed subject. One day, I was invited to a very broad audience French television show, and I knew I had just 1 minute to talk about the essence of mathematics, and I chose to bring with me 3 objects to illustrate the nature of mathematical sciences. The first one was a book, The Elements of Euclid, a book which sounds so familiar to mathematicians. This is the most edited book in the history of mathematics, but also one of the most edited books in the whole history of the world. And also, for many people like me, as a child, Euclidean mathematics, Euclidean geometry was my first contact with mathematics, with the mathematics of reasoning. The second object which I brought with me for the television show was this one, the gumbots. This Hungarian discovered solid object, which is homogeneous, which has only one stable equilibrium and one unstable equilibrium. So if I let it, put it whichever position you want on the table, it will always come back to the stable equilibrium, which is this. And there's only one unstable equilibrium, which is this kind of tip. You find all the information you want on this object. It has always fascinated audiences when I bring it live. So first was the book of Euclid, the second was the gumbots, and the third one was a very familiar object, which is a smartphone. And I argued that these 3 objects contain, with their diversity, the whole narrative of mathematics. Very ancient, like Euclid, and very ancient because mathematics is the only science in which discoveries are made for eternity. The famous declaration by Albert Einstein saying that this is the reason why mathematics is above all other sciences, that once you have established a truth in mathematics, it remains true forever. And the theorems of Euclid are still as true nowadays as they were before. But also, Euclid is the symbol of the time when mathematics ceases to be just rules for computation and solving problems, but also when it becomes science of reasoning, deduction. And with the fact that mathematics is wants extreme care in the reasoning. Mathematics is the only field of science in which 1 billion clues, all going in the right direction, in the same direction, are not sufficient to be a proof. That's the only field of mankind intellectual field. That's the only field in which you need logical reasoning and only that to establish the truth. Now, on the other hand, mathematics is not just reasoning. It's also very concrete, and that's the illustration with the smartphone or with the gumbots. The gumbot is an object. The smartphone is something which allows to do a lot of things. And in one case, the gumbot is something that is just for the art. There's no application that is known of the gumbots. Nobody has made money of it except maybe people who make the shape and can sell it to fascinated people like me. But on the other hand, you can make fortune on smartphones and on technology which is based on mathematics. And in math, you cannot distinguish the one that is just for the sake of the art and the part which is for the sake of applications. They go together. You cannot distinguish the concrete realization and the abstract reasoning. They go together. And you cannot say that there is the old mathematics and the new mathematics. They all go together, and there's a string from the ancient past to nowadays and to the future. So you have there all the diversity. Also, in the problems, there are the problems that you can ask about Euclidean geometry, about geometry of triangle, which were so fascinating for me as a student, but somebody else will be fascinated by the mysteries of the convex shapes, and the gumbots will appear like a challenge. Some other people will be fascinated with the applications of communications and cryptography and whatever. So the art, the essence of mathematics lies also in this extreme diversity of motivations and applications and of ways to do this. And whenever in a conference you insist on the beauty of mathematics, you can be sure that somebody in the audience will tell you, but you know, the important is that mathematics is useful. And whenever in a conference you insist that mathematics is useful, you can be sure that somebody will tell you, you know, the importance is that it's also beautiful. Mathematics is both science and technology, and both science and art. And no other science, certainly, is at the same time so deeply an art. Now, of course, the status of mathematician is very much influenced by the status of mathematics, and we have to remember it as mathematicians. Mathematicians are guardians of an art. They keep the recipes, the tricks, the theories. They pass it from one generation to another. They keep alive in their brains the discoveries and the recipes. But also, mathematicians are experts in finding, discovering new ideas, new concepts, new structures, new arguments. And this goes with a particular mentality, which is always on the side of challenging opinions. New mathematics is very often obtained by challenging points of view. And it's something that I experienced in my career many times as a mathematician. To make some progress, if you just follow the rules and the advice given by your advisor, you will not make progress. You may obtain new computations, new applications, but you won't have new ideas, new forms of mathematical art, new forms of reasoning. These ones come when you challenge what comes from the lesson coming from the master. And throughout the centuries, you see so many examples of mathematicians making new discoveries by challenging the theory that was known at their time, by bringing a whole new point of view to that. There are famous histories about this, famous stories, which I often tell about, for instance, in conferences. Take the history of the stability of the solar system. It's one of these cases in which new theories emerged generation after generation, and point of view changed, and so many times the generation of mathematicians thought with a viewpoint that was contrary to the one of the previous generation. It started with Kepler, discovering the famous laws of Kepler and showing the perfect, something that was like perfect harmony about the laws governing the solar system, and perfect stability with Kepler. Then it was contradicted by Lagrange and Laplace and Gauss, using brand new theory of errors and perturbation theory, masterpiece, showing that the stability had to occur over very large scales of time, like million years or something like that. But then, later, it was again contradicted by Henri Poincaré. Poincaré actually thought he started to think that he could prove the long-term stability, and then discovered, after receiving a famous prize, that in fact he could prove the possibility of instability. This was one of the most famous mistakes in the history of mathematics. And after the work of Poincaré, people believe in the instability of solar system over very large periods of time. And then in the middle of the 20th century, then come Kolmogorov, Arnold, and Moser in a beautiful work putting together classical mechanics and probability theory and Hamiltonian dynamics and a new role of probability coupled with mechanics, showing that under some assumptions not satisfied in practice, but that you could imagine apply in spirit in real life, there had to be, with large probability, forever stability. Beautiful piece of work, and then the mood of mathematicians about the stability of solar system had to swing again. And then in the 70s came people like Laskar and Tremaine, using huge computer simulations and very clever mathematical ways of rewriting the equations, showing that in practice there should be some instability after all. So from Kepler to Laskar, you see that the mood and the dominant theory about this particular problem of the solar system stability has changed many times. Each time it comes when somebody challenges the previous theory and challenges the point of view and the idea. He does not say what the previous guys did is wrong. He says, they have one point of view, but I think there's a better point of view, which is this one. And this is my set of assumptions, and I will try to convince you why it's a better representation of reality and why it's better for the prediction. This is one story. There are thousands of such stories, but this one, the one of the stability of solar system, maybe the most famous also because it's one of these problems in which trying to solve the problem has generated entire fields of mathematics, from matrix theory to perturbation theory to the development of probability theory to the development of numerical computations, numerical analysis. And this is always the interplay in mathematics. The history of problems, the history of concepts, they go hand in hand. New concepts enable to tackle new problems force you to discover new concepts. And there you go. And it's a story which is full of mistakes, full of adventure, full of unexpected things, unexpected adventures. I would say, as a consequence, a mathematician always has to be on the side of freedom of thought, freedom of speech, freedom of being able to contradict the master, because this is so much entrenched, engraved in our field. Mathematician is deeply rooted in democracy and related to democracy and the idea that everybody is allowed to contradict and to raise an objection. I realized this, not formalized like this, but I realized this very early when as a high school kid, I was confronted with mistakes of my teacher. This did happen. I remember this course in mathematics, and the teacher starts to prove some theorem, etc. And I see the theorem, I could not believe it. I was something like maybe 14 years old, something like that, 15 years old. And I said, I don't believe it. At the end of the course, I go and I see the teacher, and I tell the teacher, Madam, I think I have, there is a problem with this, with the statement that you gave us, because I think I can construct a counterexample. And I showed her the counterexample. She said, but it's strange, and I explained her, etc. And she said, oh, I had to think about it. And next day, at the next course, she told me, okay, you're right, and this is the good proof, etc. And she made a correction for the whole class. So this was an example that when you are a school kid, you are not obliged to believe in what you're told by the master. You can contradict. And if the master is of good faith, goodwill, the master will recognize that he or she is wrong. In all other sciences, this is impossible. In physics, they tell you, okay, about the existence of atoms. How can you contradict the existence of atoms? You have to believe what you are told about the experiments. In biology, they will tell you about the liver, about the biology of the whales, about the climate or whatever. And you're a school kid, how can you contradict that? You have no weapon to contradict. But in mathematics, because everything is proven by the reasoning, you have a weapon, which is your brain, your capacity of reasoning, your free spirit and ability to contradict what you are told. And if you give a proof, then you can contradict the authority. This, I told you the example of when I was a kid, but somehow it continued. This is my PhD thesis. Wow, such emotion while looking at this document in which I put all my heart. I defended my PhD when I was 25, it's not so young. And it was about partial differential equation of Boltzmann and Landau in physics theory, mathematical theory of the physics of gas and plasmas. And there are many chapters. My PhD started a bit like a joke, you know. I was the president of the students' union at the beginning of my PhD. I was not at all motivated by mathematics. And my advisor was worried about me and about when I was going to get to work. He wrote me like, it's time for you to start working. I put his small document, his small card. I reproduced it in my PhD to show people I was in a predicament in those days. And then I started to work and work and work. I started to work when I was promised a good position after my PhD at École Normale Supérieure. Anyway, I fell in love with the Boltzmann equation, which was a subject in which my PhD advisor was a very well-known master. But in my PhD, the most important parts are not the questions that were asked by my PhD advisor. These are questions that it was answer to questions that were found in the course of my PhD. In some cases, questions that my advisors liked. In some other cases, questions that my advisors did not like. Some of the techniques were radically different from the techniques of my advisor. They were inspired also by other people. My advisor was Pierre Lyons, but they were also very much inspired by Yann Grenier, by Michel Ledoux, by Eric Carlen. And I developed my own technique. At the beginning of PhD, I thought I will do the same spirit and development of what my advisor said. But by the end of my PhD, I had switched. Or I had rather put it in a different perspective and developed some alternative techniques. And there had to be in this PhD some element of rebellion for it to be a good PhD. And in science, as in the example which I told you, a good will, a good faith master will always recognize the merit of the student, even when the student does not comply to the instructions of the master. Also, I changed subjects. I went into questions that were unorthodox. I developed some old subjects, mixing it with new subjects. You know, this is the great adventure when you're a young researcher, going everywhere in the world, finding new problems, being invited here, discussing with somebody, finding out there's an interesting problem, going for another collaboration, etc., etc., etc. And this led to a number of productions and articles on new subjects. This is one of my favorites, Optimal Transport, Old and New, 1,000-page thick book, which I wrote on a subject which I did not work on at the beginning of my PhD. And I started to get in the subject as I started to work by coincidence, by accident on some bit of the subject, and was invited to some collaboration, then to give a course. Giving a course is the best way to learn your subject. And that's also one possibility in which you will grow your spirit, your free spirit and spirit of contradiction, finding for yourself which are the most important things in a subject. You need to always remember the sentence of your Cantor, the father of set theory: the essence of mathematics lies in its freedom. And it is also freedom which guided me to what may be my most famous work on Landau damping, the work that led me, clear the bar for the Fields Medal. It is quite an accident that I started to work on this problem. Nobody asked me to, of course, but I wanted to work on another problem, regularity of solutions of Boltzmann equation. Boltzmann equation is not related to Landau damping. Landau damping is related to the Vlasov equation. I wanted to work on the Boltzmann equation. I had a work session with my former student Clément Moore, with whom I wrote this paper eventually. I told him about my ideas. He told me his ideas. He said he remembered the conversation with Jan Gour from Providence, and maybe there was a relation to Landau damping. Wow, I never thought about that. What could it be? Then I remembered another conversation with a mathematician from Princeton. Then for 2 years, Clément and I struggled with that theorem, not knowing at the beginning if he wanted to prove this or that, not knowing which were the tools, and making hundreds of mistakes, some of them big, some of them tiny, and going on, correcting them, etc., etc. It was a crazy story, very fragile in the sense that many times we thought we were facing a dead end, and our proof, our reasoning could not work. In the end, it did work. Landau damping is the phenomenon of stability of plasma, very important, extremely well known in plasma physics, and very important also in applications of plasma physics, which are quite important. And it tells you that in a plasma, you have stability, even though the plasma dynamics is reversible. Reversible in the sense that there are no collisions, no increase of entropy, no row of time. So you could think that there is no going to equilibrium, because going to equilibrium in the Boltzmann equation is related to in gas dynamics is related to the arrow of time. But in Vlasov equation, there is such damping phenomenon for small perturbations. And the genius physicist Lev Landau discovered this in the 30s. It was quite a shock, quite controversial. Together with Clément, in this huge paper, eventually, we showed, using new theory, new tools, that indeed you could set the reasoning of Landau on rigorous mathematical footing, provided that you are close enough to a stable equilibrium, provided that your perturbation is smooth enough, and we explain exactly how to compute the expected smoothness that you need, making the link with the problem of Kolmogorov-Arnold-Moser, making the link with a famous experiment in plasma physics called the echo experiment, etc. And showing that various physics phenomena are related, even though this was not expected by physicists themselves. So this work was full of adventure, full of wonders, full of miraculous events, and so on. I was convinced in my heart that we would tackle and solve all the obstacles, but there was no logic about this. Some of my colleagues told me that it was so difficult, so many obstacles. How could you believe that you would solve it? This is not something rational. It's not something that you learn in school. It's something about the passion that you have inside yourself, and say, okay, I'm going to solve this mystery, and you fall in this so deeply that you become part of the problem in the sense that you want to solve the problem from within, that you are dreaming of the problem with sometimes some illuminations when you wake up at night, etc. This is the kind of extremely intense state in which you will be. I always say the three most important characteristics of a mathematician are tenacity, imagination, and rigor. Rigor comes third. It's tenacity and imagination that will make your mark and make your career in the world of mathematics. This we know when we are researchers in mathematics, but society at large is very much unaware of what it means to be a mathematician and what the real nature of mathematics, how much passion there is in it, how much surprise there is in it, how much contradiction there can be. It's very important. At a time in which society very much relies on mathematics, it's very important for us to share about the work and the role of mathematics and mathematicians. And this is what I started to do after the Fields Medal in 2010 on large scales. I wrote a book to tell about the adventure of the Landau damping problem solving. This is the book. It's called Living Theorem, or the English title is Birth of the Theorem. This is a book which is not written like a mathematics book, because there are portraits of mathematicians, there are stories like an autobiography a little bit during a short period of time, during the 2 years of working on the problem. There are email exchanges, some of them very tormented, you know. But it's not like a usual book explaining about science for broad audience, because there are also formulas. Here's a portrait of the late Carlo Cerfiniani, and I explained what was his conjecture, what were the tools that we set up to prove it, etc., etc. And also, I put in the book some of the big formulas that we have to fight with as mathematicians. And this was, you know, to show in a very impressionist way what is the life of a mathematician. Also, on the cultural aspects, like what is it that you do at night, how you work, what kind of songs you listen to, etc. There is a part of the book in which I describe a song. There is a part of the book in which I describe encounters with various mathematicians, etc., etc. This is about a song. This is about some of the formulas. You know, to show in an impressionist way the life and work of mathematicians, insisting on mathematics as not as a deterministic science, but as a passionate art. It's as if your kid wants to know about your work as mathematician. You don't try to simplify things. You bring your kid to work, and the kid will see what you're doing, with whom you're talking, how you are desperate sometimes, happy sometimes, what you're listening to, etc. The whole life of a mathematician. The book, precisely because it was an original point of view, had quite a success, was translated in many languages, including Chinese. An important thing to know about the book is that it was not my idea in the first place. It came by accident, by encountering a famous editor in a dinner before the Fields Medal. The editor was intrigued by my spider, started to engage conversation. What do you do, etc. Oh, I was told you're a famous mathematician. He wanted to have me write a book for him. But all the examples of book I could think of were of no interest for him. I can write you a book on the Boltzmann equation. I don't care. A book on the entropy. I don't care. I can write you a book on information, etc. No, he told me, I want to know how you work, how you think as a mathematician, what goes in your head. I was very much embarrassed. I thought about it, and then the result was the book. I thought, I'm going to write it. It will be what is behind the curtains when you make a discovery of a theorem, and what is the process of being a mathematician, and I will tell it like an adventure. Actually, the editor thought he could even publish it writing a novel. This was the start of many years of communication of mathematics, which I undertook in collaboration with various people, with always the same idea that to make people understand mathematics, love mathematics, don't just talk to them about how useful is mathematics. Tell them about the adventure of being a mathematician, about the art. Tell it like it's a bunch of stories. And stories always mixing three threads. The histories, the stories of people, the stories of problems, the stories of concepts. And when you make a lecture, a good lecture, it has to be these three threads together. maybe the idea of Fourier will come here in a problem, another problem, and then the problem that Fourier wanted to solve, and the life of Fourier himself, and how he was also in the revolution or after the revolution, in the empire, etc., etc. And all this making mathematics an art, a human activity, as well as a science. I did this for so many projects. For instance, this is a comic strip which I wrote with some with a great comic drawer, Edmond Baudouin, very famous. It talks about some of the some very important hidden characters during the Second World War who had a lot of influence, and their mistakes or their actions, their discoveries, the kind of spirit they were in, the kind of crazy stories they had to live, and what is in their heads when they are afraid, when they are proud, when they are ashamed, when they are full of questions, and so on. So these were Heisenberg and Turing and Szilard and Dowding, and telling this as an adventure as well as science in the construction. A little bit more crazy project made together with great photographer Lisa Rose, very particular, very special photographs, and she wanted me to write the text corresponding to the photographs, and she was attracted by collaboration with me because she thought highly of my imagination, and she thought I was ready to find some logic behind her photographs, to find some way to order them, to find some text with some kind of poetic twist, etc. This is not mathematics, of course, but is the kind of participating with the idea, insisting on the fact that mathematics come with the imagination as an art. It's also something which I insisted on a series of stand-up lectures in the Maison des Métallos Culture Hall in Paris, very much about bringing quality culture to all kinds of audience, including audience which do not usually get interested in mathematics. Here you see the gumbots on this one. This is about this is an orrery about the motion of planets, about geology. This is the clean surface with the the negative curvature, whatever. So in all these lectures, always it was about the art of it, telling stories, and always stories about that would bring together these three threads: the story of ideas, the story of people, the story of concepts. Whole book being dedicated to a very inspiring mathematical figure that was Mariam Mizrahi. So this, for a number of years, was the main of my activity, talking about mathematics, making collaborations of mathematicians with artists, finding ways to talk about problems, but also get involved in some projects, like association projects and so on, and being part of society. I strongly believe that we, as mathematicians, have to be very much inside the society. This is also something that was one of the main characteristics of the career of my PhD advisor, Pierre Williams. Learning to do mathematical communication was not immediate. I had to work hard to find my ways to do mathematical outreach, to speak about mathematics to a large audience. It was very important that for many years, I was a professor in Lyon. My neighbor was Etienne Gis, one of the first masters of mathematical communication. And at some point, he was considered the best mathematics lecturer in the world. His lectures in International Congress of Mathematicians and so on were extraordinary. And he took the job of mathematical outreach extremely seriously. And I was very much influenced by that. In Lyon, there was an atmosphere, both at the École Normale Supérieure in Lyon and in the Lyon 1 University, there was an atmosphere about sharing to the society, giving account to the society, which is legitimate for the society to ask because we are part of society, we are often funded by society, by public money, but also we need to get from the society the problem, the people, whatever. We are part of society and we need to find the good ways. My first interview for a generalist journal was a disaster. The journalist wanted to cancel the interview because it was so obscure, whatever. And then I went through, learning sessions, master classes, whatever. and was passionate about that also. I wrote in newspapers, some columns, I was on the radio, I learned a lot, and there was all these collaborations and projects which I told about. Some of the most important lessons I learned is, first, to attract your audience, you need to talk to the heart first, emotions, something which looks close to you, which will bring a link between the audience and you. Something related to the culture. Culture is what brings people together. Emotions is what brings people together. Then, after you hook your audience with these emotions, you can go on with the concepts, with the story, with the rationality, with the logics. But you have to start with the irrational, so to speak, and never separate the concept from the human context, the human adventure, and so on. This was somehow in the direction, in the continuation of my mathematical work. But then I did more than that and went further on, becoming a politician and going into politics for real in 2017. Okay, actually 2017 was not my first encounter with politics. As soon as 2010, right after the Fields Medal, I started to be engaged in a number of projects, association, institute governance, talking with people with all kinds of responsibility. I always had some taste for responsibility. This certainly goes back to the time when I was 21 years old and I had myself elected as the head of the student's office. And I liked it so much, handling the problems, finding how to try to create the cohesion. After 2010, I was involved in political groups about the construction of Europe, federalists as they are called. I still consider myself a federalist, name given to those people who believed all nations in Europe have to engage in a strong integration process so that Europe can become a strong unity, a political entity, an economical entity with some cohesion and some political structure. This was back in 2010, but this led me little by little to be more involved with the national politics. In 2017, with some complicated sequence of events, I ran for member of parliament, and I was elected. And it was a new life that started. New life in which the big problem was how to make sense of my scientific career within the political career. Convinced that it makes sense to have scientists in politics, but it's a delicate equation to find the problems and ways in which your scientific experience can be useful. International experience that goes with the research, with the problem solving, that is quite important in politics. Also the fact that politics nowadays rests a lot on very tricky scientific problems related to environment, related to epidemics, related to biology, related to energy, whatever. And in these 4 years, from 2017 to now, on some occasions I managed to make the better of my scientific experience, and on some other occasions I did not manage. Whether it was a success or a failure, it was always instructive. Some of the most important things which I think I was led to do is the mission on artificial intelligence. Before showing it to you, this is the journal in which, newspaper in which there was an interview like, live my life of member of parliament, of deputy. And it was in those days when there were many newcomers in politics in 2017, many interviews like, how is it to be in parliament? What do you think? At first in parliament, other members of parliament were looking at me like a strange beast, you know. What does this mathematician do among us? There was a time in history in which mathematicians were quite numerous and scientists were quite numerous in the French political life, but this was long ago. There are many examples long ago. Nowadays, very few examples. And one of the first missions that I was given for 6 months was a mission about artificial intelligence. This is the report which I wrote after 6 months, a report which tries to get a complete picture of artificial intelligence with consequences for France and for Europe, about data policy, about the ethics of AI, about the job future, about education, about fields of application that should have priority like health and mobility, and environment and defense. And, trying to make the big picture, the whole picture of what AI should be like and why it's the business of everybody. So this report was for writing a technical document, but also for addressing broad audience, going on the TV, talk about AI, going to newspapers, talk about AI, going to debates, talk about AI. Of course, it rested on my experience of scientist and mathematician. For instance, this is a book which I edited together with the medical doctor, Professor Bernard Nordlinger, about health and artificial intelligence. I'm running this on behalf of the Academy of Sciences, Nordlinger on behalf of the Academy of Medicine, and we organize conference, we invite lecturers, whatever. So this is the scientist part, and based on the scientist part, I wrote this report. Still nowadays, I still get asked sometimes by members of the government, sometimes by people from the industry, sometimes by just citizens about AI and what I think about this, etc. Recently, there was a delegation from people from America to talk and discuss about the American report and compare it to the French report, etc. So this is an example in which the scientific knowledge could be brought directly into the heart of policy and society problem. And the plan, which was deduced from this book, from this report, has been implemented to, in large part. Still, a number remains to be done, but let's say this became the official plan of AI for the government. Another example, which was more tricky, was a report on the teaching of mathematics, a work which I did with Charles Torossian, to show and see what we had to do to repair the French system of mathematics teaching, where were the main difficulties, how to act, training of teachers, on the curriculum, on the tools, on the ways to organize things in a high school, in a medium high school, in an elementary school, etc., etc. The report went very well. The report was very much praised by the mathematician community and by the Ministry of Education, and was started to be implemented. And then problems became. Ministry of Education did not implement just our report, also a number of other things which had some constraints, which were determined by this or that, etc., etc. Enormous number of difficulties arose, in which I had no role and no part, in which I did write some warnings for the government and say, okay, be careful about this or that, but in which, in the end, situation is extremely confused right now, in particular among mathematicians and mathematics teachers. It's good to write a report, but you always have to remember implementation is much more difficult. And I did regret that I was not more involved in the implementation in this case, with maybe some misunderstanding that could have been avoided. And currently, a big number of things to fix still in the mathematics strategy. Another of the things which I did, and which I think was badly needed, was the reform of the Scientific Parliamentary Office. Scientific Parliamentary Office, or more precisely, Parliamentary Office of Evaluation of Scientific and Technological Choices, is a group made of 18 members of a National Assembly and 18 members of Senate, so both chambers of the Parliament, working on problems which are of scientific and technological nature, important for enlightening the choice of the politics on it. Say, politicians have to make choice about nuclear energy, but this is a highly technical subject in which you need the opinions of many scientists and need to organize some contradictory debates and also to hear the point of view from the society, etc., etc. That's the role of the Scientific Parliamentary Office. Organize this debate on problems which are the interface of science and politics. And it was founded in the 80s. It was founded precisely to work on subjects related to nuclear energy. So I became president of this office. Currently, I am the president of this office. And I worked a lot to diversify the themes of the office, to hire scientists within this parliamentary office, to go more in the directions of humans and social sciences, to get more in association with the groups, the working groups of the parliament, to follow more closely the pace of political events, etc. Quite a work. What subject did we treat recently? Things such as research in polar environment, long-term COVID, or scientific integrity, or viruses attacking bacteria and what we can do about these viruses to use them to help fight bacterial diseases, or quantum computing and quantum information and quantum cryptography, or open science, or all kinds of therapeutic subjects, therapy subjects against the COVID, you name it. One of the most tricky subjects which we had to handle is about the new breeding technologies. These new techniques of biotechnology based on editing genome techniques such as CRISPR-Cas9 to edit the genomes of plants. So there are aspects related to biology, related to economics, related to ethics, lots and lots of debates. In this case, for the NBT, it was a very hot debate. The two parliament members who were responsible of the subject had conflicting opinions, could not get together, and I, as a president of the office, had to, step in and organize a synthesis with the help of the scientists within the secretariat. And we were discussing for a long time on each subject, and we arrived in formulating 7 propositions, 7 recommendations. The two responsible people agreed on 6 of the 7 problems, 6 of the 7 recommendations. And the last one, the 7th one, they had conflicting opinions, and we could exactly pinpoint why and what kind of differing values it corresponded to. Then we had made our job. That this is a problem. We have not taken a decision because it's for the democratic decision to proceed. But we studied the subject and analyzed it to the point where a political decision becomes possible. So we analyze the possible choices. Here's the choice, and now you choose between this that has these consequences and that which has these consequences. Balancing the various problems and advantages or drawbacks. Balances the natural sciences with the human sciences. And the common feature with all these problems, in fact, is that most tricky parts are those related to social and human sciences, like opinion issues, bubbles of information, fake news. In science, we're used to the idea that no one a priori has the truth. You have to listen to all the contradictions. Even a revered scientist can make mistakes, and there are famous examples in the history of science in which the best scientist of the world makes a horrible mistake, and in fact, some of his opponents was right. We have to know such examples. Eventually, all these problems get resolved in the right direction, but sometimes it takes time. But one should never, a priori, believe as a God-given truth what somebody or some entity or some institution or some political party says. One always has to think, is this really true? Can I contradict? Where is the logical reasoning, etc., etc. That's what we do at Scientific Parliamentary Office, organizing the political debate, which is the basis of the democracy. Democracy, the heart of democracy, is the contradictory, open, sincere debate of ideas. And I tell you, and this will be my conclusion, in a world in which debates of ideas are extremely confused, in a world in which many political problems hugely rely on scientific and technological advances and choices, in a world in which science is hugely used by the power, we scientists have a huge responsibility to get committed in the world and to make sure that we keep the memory of the past and everything that we can learn from the past, from the history of sciences, from the history of mankind, and that we get committed to making our vision of the future explicit, saying which are the consequences of the choices that we will make, consequences on our children, what we should transmit to the next generation, currently more than ever, and in a world which is more mathematical than ever, with the advent of information technologies, of statistics everywhere, of artificial intelligence, you name it, all kinds of mathematical applications in the world, we mathematicians have a responsibility of being committed to the society for the future and for the sake of the future generations. Thank you for listening.